Now, here children, that the topic 1.5.2 turning effect. Our topic for today's discussion is turning effect. Now, students, before I move to turning effect, just let me give you a one example. Example is, suppose kinematic we already have studied. In kinematic, we have seen if I have this object, and on this object, if I push or pull with a certain force, then due to this force, if this force is sufficiently higher than the force of friction, then what happens? This object will move either to the right side or to the left side, depending upon the direction of applied force. So basically what's happening? Linear motion is taking place. Linear motion, rectilinear motion, linear motion is there due to the effect of this force. Now think about, children, think about the situation that always, is it always possible that if you apply a force and the object will move in a straight direction? Is it the case, children? When you apply a force on an object, that object will always move in a straight line? If you're thinking yes, then your answer is wrong. If you're thinking no, force is not necessarily that the force is always make object to move in a linear path. Objects rotate. Object also rotates due to the effect of force. One example I want to show you. Look at the spanner. Now see, I have a spanner in my hand. This is a spanner. And here you can see on the screen also, this is a spanner. On this spanner, you know, the basic purpose spanner is what? To lose or tighten, you know, nuts or screw. Okay, to close and to open nuts with the help of spanner. Spanners can come in the different length, smaller one, longer length. So here in this spanner, children, if I apply a force, now I am going to apply a force here. So nut, I consider my finger. And now here, if I apply a force, I am applying a force with my right hand. And the effect of this force, you can see the spanner rotate about an axis, about the nut. Maybe clockwise or maybe anti-clockwise, depending upon the situation. We are going to open or close the nut. Another example, children, another case that if you have seen, when you open a jar of food here, a foods, you know, I have this a protein powder box. Now on this protein powder box, on this box, if I apply a force with my hand, I'm going to apply it. Now the lid is closed, so I want to open. I'm applying a force in the anti-clockwise direction. I have applied a force, and then the result is that this object will rotate. So remember, my dear children, force is not always make object to move in a linear or a straight path. It also make object to turn. And this phenomena, you know, movements, turning effect and turning forces and movements. What is this movement, children? Turning effect of a force is called movement. Student, please note it down. Turning effect of a force is called movement. Movement, M-O-M-E-N-T, movement. Turning force is called a movement. Means when you apply a force on an object in such a way that the object rotate about an axis. One example, one more example, children, I want to give it to you. Seesaw. In seesaw, you know, children, everybody, you know, that when we all were kids, okay, children, and at that time we always like to visit a park. And if we visit a park, then, you know, our tendency is inclined towards to go and sit on and enjoy on the seesaw. What is the seesaw, you know, children? Let me draw. Like here, this is a a simple example of a seesaw. This is a point of pivot. About this, the seesaw, move or rotate. But what happens, children, if someone sit, okay, so instead of drawing a boy or girl, so let me put a weight on the right hand side or onto the left hand side. Due to this weight, it has some mass, gravity, so weight is there. So due to this weight, now the person who is sitting on the right hand side, due to his her weight, that what will happen? What will happen, children? Let me draw another situation. This will, the seesaw will rotate. If I consider this is the point P, where this point P is perpendicular to the plane of my laptop screen, and the seesaw will rotate about the fixed point P, either to the clockwise or to the anti-clockwise direction, depending upon where we are have placed the object or weight. So this, again, children, effect of this weight, effect of a force, object rotate, and this turning effect of force is called, again, children, what? This is called the moment. Moment of force have another name, and that is called torque, children. Torque. T-O-R-Q-U-E. Another name of moment of force, or either you can call torque. T-O-R-Q-U-E. Torque. And to write in a symbolical form, generally we use this torque, this symbol. It's a Greek letter. This is a Greek letter tau. Tau. This one, children, like this. It's a Greek letter. So torque. Let me move ahead. Now here, children, in understanding this topic of torque or moment, that is the turning effect of force, I want to give you two more important points, children. And what is the point? And the point is, children, just wait a minute. It has goals. Yeah, I'm here. Now, children, that to understand this topic clearly, I want to give you one more example, children. In turning effect, children, if you apply a large force, then the turning effect will be higher. For example, students, now I want to show you one more example. I have to just move from my position here. I want to show door. I want to show a door at my room here. And now, see, just wait a minute. Now, what happens? If you can see, this is a door, and the handle, please, okay, just focus here on the handle. On the handle of the door, the knob, if I apply a force, children, if I apply a force, what happens? Look carefully. If I apply a force here on this door, then door open. We can open, we can close when I apply a force. And here what's happening, children, that this door is rotating where? About the axis, about this axis, about the hinges, children, about this hinges. Again. If I apply a force, look here. If I apply a force, then the door rotate about this axis of rotation. Sometimes you think if I apply a force on this door, and that will make a linear. This is not a linear motion, children. It's not a linear. if you keep applying a force on this door, then you will find this door is in rotational motion. This door is rotating about the axis, about this hinges, this part, children, about the axis, on this axis. And now in this case, children, suppose if I apply a force here, then greater the force, greater will be the turning effect. If I apply a large force, for example, if a kid is here in my room, a kid means a child, maybe of 10 years. So if that boy apply a force on this knob, on handle, and take another example, if a man, an adult person apply a force, then there is a difference, there will be a difference. Kids will apply a different kind of force, the man will apply a different kind of force. And when a man adult apply a force on the door, it's easy for a man to open the door. But on the other side, children, take one more example. Why these handles are provided here? Why these handles are provided here? Why this handle is not at the middle of the door? Why this handle is not here, children? Why it is at the extreme edges of a door? Why it is here? So now, children, if I apply a force here, suppose this handle is not here, this knob is not here, but it is here. So I need to apply a larger force to open the door. Children. Okay, so let me move. So basically, from this observation, children, you have to understand what? The turning effect, it depends on two factors. The first factor is force. Let me go back to the screen. Turning effect of force, it depends upon two factors. One, size of the force, children. And the second, the distance of the force from the pivot. Pivot means, children, from the axis of rotation. Pivot, P-I-V-O-T. Pivot means after the effect of force, about what axis that the object is moving, rotating actually. So turning effect, if it is depending upon two factors, so I can write an equation that the torque, children, remember torque, I will write this Greek letter, torque, remember torque or moment or force, both are same. This is equal to force and multiplied by distance. Basically, it is a perpendicular distance. Perpendicular distance from where, children? Remember, perpendicular distance, you can see here, from pivot, from the axis of rotation. And so this perpendicular distance I can take by the letter R or D, distance, perpendicular distance. It is distance from the axis of rotation. So the question, children, that I asked you, why these door handles are provided, or the knobs are provided at the edges? These are always at the extreme end of the door, not in the middle, so that R will be larger and larger. If R is higher, perpendicular distance from the application of force is higher, from the axis of rotation, if it is higher, so it will make turning effect will be higher, means torque will be higher, and easily you can open or close the door, means you can easily rotate the object clearly. Sometimes, children, smaller length of spanners are not able to open the screw or nuts. If you have seen that sometimes to open the change the the wheels, punctured wheels in our car, we need spanners, and these spanners are of larger length, of a longer length. Longer length means, children, again the concept, longer length of spanner means R from the axis. Axis what? Nuts, in case of when we are going to replace the tire, okay, from the puncture tire in the car. R is large, turning effect will be higher, that will make to unscrew the nuts from the car. So that is the one thing, children. One more point you have to remember. Come to about the unit of moment. If the equation of moment is force and perpendicular distance from the pivot, so it means SI unit of force we know Newton, SI unit of distance is meter. So Newton multiplied by meter is the unit of moment. Please remember. Now children, I want to give you one example here. You look at this screen, example number 1, that whatever we have discussed here. Now that the concept of moment I have discussed with you, but let us practice some questions. Then again, I will come back to the topic of moment. Calculate the moment of the force on the nut in figure 1. Okay, in figure 1, I have to go back. This is our figure number 1. What do you have to calculate, children? Moment of force. Where? Moment of the force on the nut. Now see, moment of force, children, I know moment is given by torque F into F multiplied by R. Where is the force, children? You can see this is the force, which is 20 Newton. This force is acting perpendicular to the axis of rotation. Means, what is the R? R is the distance. Remember, children, what is R? R is the distance between force and from the axis of rotation. So here it is given 0.1 meter. This distance about, this is the pivot about which that the nut will screw, means rotate, multiplied by 0.1. So 0.1 I can write 1 by 10, 1 0 cancel out. So this 2 Newton meter is the turning effect of that force. So due to this 2 Newton meter, that is the torque, this you can open or close, loose or tighten this nut. This is the way, children. Okay, next question. Here in example number 2, figure 2. What about a situation where there is more than one force trying to rotate an object? Now, instead of till now we have discussed that there is a one kind of force. The situation may arise, children, that the two forces are there, and what happens then? Same example, children, in seesaw, always two children are required to play, and so here in this example, children, on the screen, we have given one object on the left hand side, another object on the right hand side. Pivot is the, remember this, children, this is the pivot point about which these two weights, they will rotate. On the left hand side, a force of 5 Newton is acting, children. On the right hand side, a force of 8 Newton is acting downward. So remember, there will be other cases. These forces may be upward, these forces may be downward, one force upward, another force downward. So there will be a different kind of questions you will find. Their distance is given from the, remember, children, distance is always from the pivot and from the force. 20 centimeter. Right hand side object is placed at a distance of 25 centimeters from the pivot. Now, please find moment in both these cases. Let me find that the moment of left hand side object means moment of 5 Newton force. Moment of 5 Newton force, you know what is that value? Force is 5 multiplied by, children, multiplied by what? Yon Kim, multiplied by
20 centimeter.
Moment, we are finding the moment of 5 Newton force. And not received answer from UNK. Moment is given by force into perpendicular distance from the pivot. So 5 Newton force is here. What is its distance from the pivot?
20 centimeter.
20 centimeter. I got an answer in chat, folks. Here one said 0.2. 20 centimeter should be converted into meter because force in Newton. So the distances should be also in SI system, and in SI distance is in meter. So 20 divided by 100, that is 0.2. So this is the value of this Newton meter moment of force in the left hand side. And remember, children, due to this moment, due to this turning effect, this object will try to rotate in what direction? You know, children, X is force acting 5 Newton on this side, left hand side. Due to this, it will try to rotate in anti-clockwise direction. You remember, children, moments is a vector quantity. Either it can be clockwise or anti-clockwise. So here, due to the weight on the left hand side, due to a force of 5 Newton acting on the left hand side, at a distance of 20 centimeter, this object will rotate about the pivot in the anti-clockwise direction. Look at the second end, the second force of 8 Newton, children. In the 8 Newton force, you have to calculate movement. So let me write again. The torque is F into R. Force is 8 multiplied by 25 divided by 100. That is 0.25. You multiply and this answer is in Newton meter. So due to this amount of torque, the object will rotate about the pivot. And in what direction, children? Clockwise or anti-clockwise? See the impact of this force. This person having weight 8 Newton on the right hand side about the pivot point will make the axis, it will go down and it will try to rotate in the clockwise direction, children. Let me move ahead. So this is the way, children, that how you can find out the turning effective force as per the given information. Now, children, next important point that I want to discuss with this is principle of moments. Principle of moments. On what principle that these object rotate? And principle of moment is basically about the equilibrium. In what condition that the beam will be in equilibrium, children? In what condition that the beam will be in equilibrium? Equilibrium means, children, the net turning effect of force is zero. Listen carefully, children. Principle of moment, it states that is basically that if you are interested to make the beam or rod or seesaw balance conditions. Balance condition means it won't move upward or downward, means won't move clockwise or anti-clockwise, it remains stationary. So in that situation, the principle is that the total clockwise movement, children, total clockwise movement, it must be equal to the total anti-clockwise movement. The total word, they have used the total word. It's not only one object. You can find a situation that 2-3 objects are placed on the left hand side, 2-3 objects are placed on the right hand side of the pivot. So total clockwise movement or the total anti-clockwise movement, if they are equal, and or this total clockwise and anti-clockwise movement, that you can write that the sum of all moments, if it is equal to 0, then the condition is equilibrium. Equilibrium. Balance condition. Equilibrium means that the balance. Neither the object will move, rotate to the left or to the right. Neither clockwise, neither anti-clockwise. So this principle, please remember, this is very, very important equation, that the total clockwise movement should be equal to the anti-clockwise movement. Now see this example, children. In this example, look at the red and green box problem again in figure number 3. And where do we need to move the red box to balance the beam? I'm interested to balance this beam. I'm interested to balance this beam, children. But here the distance is unknown. I'm looking for where should be placed. It is placed here, here, here. Where this red object should be placed, that this beam will be in equilibrium. So to be in equilibrium, students, how will you find out that distance? To find the answer, you have to apply the use of principle of moment that says total clockwise movement is equal to anti-clockwise movement. Now look at the left hand side box, green box, children. Find the moment of green box. So let me write TG, that the torque acting on the green box. This is equal to force multiplied by distance, children. This is 5 into 20 by 100. So this is 5 to the, and my calculation is correct. So this is 1 Newton meter is the torque acting on the green box, and due to that, this will rotate in the anti-clockwise direction. In the second case, distance is unknown. Still, I can find the turning effect on the red box that is given by force is 8 Newton. Distance, I'm not sure. So I will take that distance is unknown, which is supposed D. That just consider that I place the red box at a distance D from the pivot point. So here in the right hand side, on the red box, this will make to rotate in the clockwise direction, children, about the pivot point. So now apply the principle of moment that states if you want the object to be in equilibrium, then the clockwise moment should be equal to anti-clockwise moment. So we have the condition of the balance, that I can equate 1 Newton meter is equal to 8 into D. So here D I can calculate. D is equal to what, children? Now here distance should be into meter, and this D is equal to 1 by 8. 1 by 8 is equal to how much? Is my calculation is correct, children?
Yes, sir. It's 0.125.
So 1 by 8 is how much? Please someone divide. And let me check the answer here if it is given or not. So solution is there. 1 into this 1 by 8 is equal to 0.125 meter, or in centimeter 12.5 centimeter, children. So that is the answer. Means that object should be placed, the red box should be placed at a distance of 12 and a half. Suppose this is the position. This is 12.5 centimeter. So that is the position where the beam will be balanced. I received one answer here. 1 divided by 2 is 0.125. Okay. Thank you, Kim. Maybe our children, suppose distance is given. You will find some situation, distance is given, but force is unknown. What amount of force should be applied that I can maintain that the beam should be in balance condition? Again, moment of force principle you have to apply. Clockwise moment should be equal to the anti-clockwise moment. Okay, 3 factors will be given. 1 unknown factors you can easily find out from it. Now, children, that look at some simulation, that whatever we have spoke, and 3.5 minutes are there. I want to give you some simulation to understand the concept of moment. Forces level, let me take, and rulers I want to take here. Now, suppose, children, if I take a 5 kilogram box and placed exact on the 2 meter distance from the pivot, and another 5 kilogram object placed on the 2 meter distance from the axis or from the pivot. Now what will happen? See what will happen, children? You can see that the beam is in balance. Why it is balanced? Because the resultant of turning effect is 0. Anti-clockwise moment is equal to the clockwise moment. Both are same position, their turning effect is 0. But if I remove this one, this is not in balance condition, because on the left hand side there is no weight. But if I place this 5 kilogram object somewhere 1.5, still the clockwise movement is higher. You know, children, clockwise movement is higher because 5 kilogram weight, but its distance from the axis of rotation is highest as compared to, still weight is same, but the distance from the pivot is small. I told you, children, that the turning effect, it depends upon the 2 factors, force and then distance. So maybe if I want to balance this condition, this box, irrespective of, I can place the object again at the 1.5 position. You can see slightly and slowly this beam again get balanced. So these are the situation, children, that you can find out how to make balance. Suppose instead of taking 5 kilogram, if I take 10 kilogram is placed here, is there any situation that I can balance this 10 kilogram with 5 kilogram, children? Is there any position that where can I balance? Is there any position? In this case, if 10 kilogram is placed at 1 meter, that will be in the balance condition. We can cross verify, children. Look here. Let me try. So on the left hand side, so instead of taking 5 kilogram, I will consider this is 5 Newton. Okay, to make my calculation easy, instead of multiplying with the gravity. So let's suppose this is 10 Newton and 5 Newton. So moment at the left hand side, children, left hand side, this is equal to force, and its distance from the pivot is 2 meter, 5 to the 10 Newton. And on the right hand side, suppose the distance is unknown. Suppose I don't know where should be placed this 10 kilogram, that the object in balance condition. So torque on the right hand side, this is 10 Newton multiplied by distance is unknown. Suppose that is D. In balance condition, you have to apply the principle